This geological map highlights the location of the Iberian Massif and, extending across the southeastern margin of the Iberian Plate, the Betic Mountain Range. Zooming in on the map, we can divide the Betic Range into two broad structural units, the internal zones along the coast, and a northern belt known as the external zones, which further splits into the pre-Betic and sub-Betic regions. This cross-section across Jaén reveals a highly deformed and stacked rock sequence. We find massive allochthonous units resting dozens of kilometers from their origins, separated by large décollement thrusts, horizontal fracture planes where upper layers slid entirely over those beneath. To understand the forces that built this architecture, geologists have to mentally reverse 185 million years of tectonic compression. We will trace the kinematic evolution of the entire region, starting from the initial rifting of the crust, tracking the sedimentary filling of those new basins, and ending with their ultimate structural collapse. The Betic Mountain Range is a shattered and inverted continental margin, preserved in a state of extreme tectonic displacement. This paleogeographic reconstruction establishes the baseline of the region, showing the Variscan Paleozoic basement acting as the foundation. Resting unconformably directly on top of that basement is the first phase of post-Variscan sedimentation, the Triassic facies. Within this sequence is the Keuper facies, comprised almost entirely of siliciclastic evaporitic clays. These Keuper clays form a highly plastic layer that will become mechanically critical millions of years later. Advancing the timeline to the early Cretaceous, the region experienced the onset of North Atlantic rifting. This massive extension applied intense lateral stress across the entire South Iberian margin. The geometry of the new fractures was dictated by pre-existing late Variscan structures within the basement, which reactivated under the stretching tension. The continuous crust broke apart into distinct adjacent elevated shelves and deep, subsident half-grabens. This rift-driven bathymetry acted as the ultimate control mechanism for all subsequent Mesozoic sedimentation across the region. This cross-section reconstructs the faulted South Iberian margin during the Aptian Albian. Closest to the foreland is the Pre-Betic Zone, the autochthonous shelf, featuring shallow marine conditions and continuous carbonate sedimentation. Moving offshore, the floor drops into the intermediate domain, a deeper adjacent basin. The Toral Formation found in this domain acted as a prime repository for deep-water carbonate turbidites. This field photograph shows the physical evidence of these turbidites, revealing the rhythmic, stacked sequences generated by submarine fans. These specific beds exhibit the Buma sequence, indicating they were deposited by rapid, gravity-driven underwater currents pouring into the basin. Shifting focus further outboard to the sub-Betic zone, the environment fractured into extremely deep pelagic basins, separated by elevated thresholds. We define these sub-Betic pelagic thresholds as isolated underwater topographic highs situated far from terrestrial sediment sources. This field sample reveals the Ammonetico-Rosso facies, recovered directly from these thresholds. These nodular, heavily pitted pelagic limestones indicate extensive intervals of incredibly slow, highly condensed sedimentation out in the deep open ocean. These extreme lithological contrasts, from shallop shelves to turbidite channels to starved pelagic highs, serve as direct proxies for the differential subsidence mapped across the Mesozoic rift. During the Jurassic period, the middle sub-Betic remained in a highly active tectonic state. Basaltic effusions erupted from the seafloor, creating towering submarine guyots. Because these guyots reached toward the surface, they allowed shallow carbonate shelves to develop anomalously within deep-water domains. Meanwhile, chronic seismic activity along the rift's fault lines created severe structural instability. This triggered frequent mass wasting events, massive, catastrophic submarine landslides occurring directly on the heavily steepened slopes of the half-gravens. This photograph captures field evidence of these events preserved as wavy, folded slumps in the Keuper Formation. Below these folds, you can trace the unconformable detachment scars where the rock sheared off and slid downslope. The chaotic sedimentary folding you see here occurs when soft, semi-consolidated sedimentary beds violently crumple and fold upon themselves during a submarine slide. The deep marine sedimentary record is a chaotic, dynamic archive of the margin's violent tectonic evolution. Transitioning to the Tertiary period, the tectonic regime inverted. The African plate drove northward, applying massive compressive stress. This forced the Mesozoic sedimentary packages to completely detach from the Variscan basement. The cause was the plastic Triassic clays, acting as a regional slip plane. In a sequential overthrust, the internal sub-Betic was forced up and over the external sub-Betic. Then came the final cataclysmic push, violently thrusting the massive combined sub-Betic rock units horizontally over the stable pre-Betic foreland, permanently rewriting the landscape. This specific mechanical failure along the Triassic layer provides the exact engineering cause for the chaotic, stacked architecture observed in the region today. Following this collapse, millions of years of top-down erosion acted directly on these newly stacked thrust sheets. This erosion created tectonic windows, specific geographic anomalies where upper rock layers have been entirely worn away, exposing rocks underneath. This photograph of the mountain peak at Valdepeñas de Jaén provides a premier example of this phenomenon. Erosion has stripped away the resistant, older Jurassic limestones in the valleys, exposing the softer, younger Cretaceous rocks beneath them. Finding older Jurassic blocks resting physically on top of younger Cretaceous rocks proves the allochthonous overthrusting model. The Betic Mountain Range remains a record of a fully inverted continental margin, where deep-water turbidites and pelagic thresholds now sit miles above their original structural positions.